All right, everybody. My walk might be a little fast, but let's go ahead and get started. Let's get started, guys. Woo. Excuse me. Hey, let's get started. So, I'm sorry I wasn't able to join you on Tuesday. I had a cold I was still recovering from, still am. I apologize if I'm not able to project as well as I normally do. I'll do my best, but I'm still not back to 100%. So if I'm speaking softly, I apologize. EQ or something that I need to speak up, but also if I pass out and just fall on the ground, just leave me there for a little while. You can go home and it's fine. But it's good to be back with you. I'm curious how the in-class lab went on Tuesday. Was it a complete disaster like before?
Yes.
Yes. It was a complete disaster.
Yes.
Slightly better.
Slightly better.
Okay, what went wrong?
We didn't know about it in advance.
Actually get it running.
You what?
Autopsy was a nightmare to install and get running.
Oh, dang it. Oh, Linux? Yes. Yeah, Linux. Yeah, so
We were told to use Linux.
what? Okay, well, I'm sorry. I tried. So here's the thing about sleuthkit and autopsy. Sleuthkit and autopsy used to be cross-platform compatible for Linux and Windows, and then they decided to completely revamp the graphical user interface. And in doing so, they decided to just support Windows so that they could make it look better. So autopsy is really only usable in Windows. Was it the tutorial online that said to use Linux, or was it the TAs?
Tutorial presented it as all three platforms.
Okay. I'm sorry. It was one of those situations where I was starting to feel better, but I knew that if I came and lectured, it would wipe me out completely, and it wouldn't be a very good lecture anyway. So that was my attempt to kind of redeem Lab 1, myself from Lab 1, while still not having to be here. So I apologize again. We're going to do another in-class lab on Tuesday. It's a pretty short one, and it has to do with the topic that we're going to talk about today. So, and even if no other software works, as long as you can get a good hex editor, you should be able to get the gist of the lab. Yeah.
What software or tooling should we expect to have installed so that we don't just have to use the text editor?
So if you have a Windows machine and want to install Autopsy, that would be a great option to use your own machine for the lab. That should work. I'll tell my team. So the TAs are working on the image that you'll actually be analyzing, and I want them to make it already in not a raw format, but a processed format. So like AFF. So that should speed up how much that should reduce the amount of time it takes Autopsy to process the image and be ready for you to actually start doing analysis with them. So Autopsy and hex editor should do you well for the next lab. Yeah, question?
Can you maybe post the image on
Post the what?
like the image file we're trying to analyze? Can you post it on the browser or something somewhere else chasing it?
Yeah, yes. Yeah, I will be posting the link on probably on my website. Or I will have like a condensed URL in a slide, something like that. Any other concerns? Couple of administrative things to take care of. First of all, happy Pi Day. Yeah. So in case you have been living under a rock or something and don't know, today is March 14th. And in the US, we write our dates like the month and then the day. So 3/14, happy Pi Day. So go have a pizza or a pie or whatever kind of pie you want, because yay math, right? Okay. Couple upcoming deadlines to make sure that you're keeping in mind. The first is there is the checkpoint for the group project is coming up on March 28th. And if you remember, we're just making sure that you're actually making progress. This is not going towards your final grade for the project. Maybe I shouldn't have said that to motivate you more. It's really just you need to make sure you have some rudimentary functionality programmed into your project at this point. Otherwise, it's just going to be too hard to complete on time. So you might remember that I said that I had 2 more programming assignments to give you right after spring break. I decided to not do those 2 because, number one, they were written for Pathward 2, and I would rather you spend your time on other things, because we're going to talk about email forensics really soon, and I have a programming assignment I want to do for that. So in the meantime, keep working on the group project. There have been some really great questions on Piazza about the group project in the last week or so. So make sure you're checking Piazza for posts related to that, because other people probably had the same questions you had. Yeah, what's up?
Will we expect grade scope be set up for the group project in the near future, or? So like a lot
in the
of
near
questions.
future, yes, sometime in the next 300 days, it will be set up.
Oh, okay. Well, I'm just saying, like, I can ask a bunch of questions, but if grade scope outline, what specific output are you looking for, then I don't have to ask it.
Gotcha. Yeah. I will bring that up with the TAs. Okay. Speaking of grade scope, some of you may have seen that your grade may have gone down a little bit for homework 1. What happened there was that SOQA built a new image that had 4 partitions instead of just 3. And some people only wrote their program to process 3. I think that's a little bit tricky with SOQA, but I'm sticking with them. That's your grade for homework 1. Because if you forgot to process 4 partitions, you kind of missed the point of processing the partition table. So, sorry, that was a little bit of a tangent. But the other deadline I want to make sure you keep in mind is that your paper reports and presentation slides are due on April 4th. Okay, so that also includes your reports if you're going to do extra credit, like an extra credit report. And remember, if you decide at the last minute that you want to do a second report for extra credit, you don't even need to ask me for permission. Just do the report and submit it to the extra credit assignment in Gradescope. Okay. Any questions about that? Yes.
If we're already presenting for extra credit, can we also do a report?
Oh, double extra credit? That's what you want?
At the very last minute.
Yeah, because that's what I like to do on my spare time. No. My gut tells me that would be unfair. Yeah.
We're presenting, we don't have to like turn into a slide stuff.
Yes, you do. That's why I did a dramatic pause. Your report and slides are due on April 4th. So the reason for that is I don't want there to be an unfair advantage for the people presenting 10 days earlier than some other people. So yes, I do want your slides.
And the slides be amended. Like if they're unfinished.
Like you submit a title slide and then later you turn the rest. So I understand what you're wanting,
Yeah.
and I just can't give it to you. I can't give it to you and be fair. This is the most fair way that I can think of, because okay, let's say this. You send in your slides, and then a couple days later, because I have like a lead time to allow people to turn it in late before the first presentation, right? So during that time, you're like, oh, I needed this. Reach out to me, okay? So some of the biggest grading problems this semester have been caused by people not talking to me, by not asking questions, by not telling me what their situation is, until it's too late for me to help them. So reach out to me, let me know why you need to make amendments, and I'll make a decision in the moment as to whether I'll. What I'm going for is there to be a level playing field, grading one presentation versus another. That's what I'm going for. Any other questions about? Yes.
Does this mean you'll have the copy of our slides when we go to?
Yes. Yeah. Yeah. Most likely, what we'll do is just load them up on the computer here, and they'll be ready for you. Any other questions? Okay, two more quick things. A week from today, we have Mike Lombardi coming to give a guest lecture. I actually talked to him for the first time last night. So yes, he is coming, and he has a lot of really great industry experience doing incident response and what that process looks like in the real world. And that's what he's going to talk about. So it'll be a really great talk, so make sure you're there. And then after today, 5 more lectures. That's more for me than for you. I'm excited that I only have to fill 5 more lectures. So anyway, that just so that's on your radar. Okay. Any other questions before we jump into the lecture for today? At least one. Yeah, I don't know. We might do a second one on, so we're talking about image forensics today. I want to do a lab within image forensics, but I also have stuff to do mobile device forensics lab. It's kind of dated, but it might still be worth our time. Okay, let's talk about image forensics. So, we've covered the basics in forensics. If all you learned about forensics is the stuff that we talked about thus far, you would do well. As far as like talking with people about forensics and sounding like you know what you're talking about and getting along well. So these last few topics that we're going to cover in the class we're just going to make sure that you have the technical understanding in that topic that you could possibly start in a new research direction or find more papers in that direction or something like that. We're not going to go as deep as we did with like ext4. We went really deep, well, medium deep actually. We went medium deep with ext4, talked a lot about data structures and stuff like that. We're not going to go quite that deep with the remaining topics. So today we're talking about image forensics. When I say image forensics, what that means is graphics on graphic files on a computer. So we're going to talk about what graphics files are and the different types of graphic file formats, different types of data compression, just at a high level. I'm not going to quiz you about give me all the versions, all the lossless image file type, nothing like that. And then how to locate and recover graphics files. But I want to frame this just a little bit more in some context. So imagine you're examining a disk as part of an investigation. What are some reasons why you might think you would be looking for graphics files as part of your investigation? Yeah, okay, yes, so you can't grep or do a string search for graphics, so we need to have a different way of looking at, okay, yep. What might we be looking for? Yes? Photo evidence that might incriminate someone, can you give me an example?
Yes, if someone is stupid enough to take a picture of himself.
Yeah, so just for the people on YouTube, because you got a really soft voice, and it's totally fine. If someone was stupid enough to take a picture of themselves committing a crime, I think you'd be surprised how often that happens. I wish we had asked Agent Gibbs that question, because I bet she would have rolled her eyes and said, "Yeah, criminals are stupid," because I've heard her say that lots of times. Did you have more that you wanted to say?
I guess another one could be like, if the image itself was like something that was illegal, so out for another.
Yes. Yes. So very good. The image itself might be what constitutes a crime, and actually your lab falls under that. The in-class lab that we'll do falls under that category. Yeah.
Maybe it's like important, someone took surveillance of someone else, and now bad guys took it, tried to destroy it, and now we want to get that surveillance back. Let's see what actually happened.
Okay. Yeah. Cool. I like these what-if scenario exercise. Any other ideas you can think of? Yeah.
Steganography.
Tell us what steganography is.
Steganography pretty much is hiding information inside the picture that is not visible to the naked eye,
Yes.
usually.
Yes.
And another would be, I think, using the image as a medium of transfer of like viruses, like hooking a virus onto it. So if somebody opens a picture, they see a picture, but they've accidentally run a virus on it.
Yes, very good. Those are all really great reasons why you would want to do forensics on images. Okay, great. Let's get in it. So to baseline our knowledge, we've done that a lot in this class. Let's make sure that we have some key terms defined and we all understand what they mean. A pixel is an element of a picture that is the smallest unit that can be displayed on a screen. That's what we're going to call a pixel, right? Now, simple graphics can be black and white, where 0 represents white and 1 represents black. The 0 and 1, think of color or not color. Well, actually, why would it be? Sorry, now that I'm thinking it, let's just take it at face value, okay? This is just one potential way of encoding an image, okay? So let's take, for example, this. Can you see what the image is?
A circle.
If you're far enough back and you kind of squint your eyes, you can see a circle. What else can you see?
Face.
A face.
It's a circle though.
Circles.
What?
Smiley face.
Smiley face? Yeah, the word happy underneath. Yeah. So if we take the ones and zeros and actually use the 0 to represent a white square and a 1 to represent a black square, place it in a grid like this, you can see that we have a smiley face and the word happy in cursive, right? So this is just one example of how you might encode an image into a binary format, okay? And then recognize here also that we have a decoding method that tells us what, where each of those pieces of data goes and what it means, how to render it, okay? All right, so one important aspect about graphics that affects the way that it looks and the amount of data that it can contain is something called bit depth. So this means the number of bits that are used to represent each pixel. So for example, what we just saw was we had 1 bit per pixel, and all we could represent was black and white, right? Because 1 bit, we have 2 values. So black, white, that's it. But there's other levels of bit depth. So 4 bits would be 16 colors, 8 bits would be 256, 16 bits would be 65,000, and 24 bits, 16 million, right? So once you get up to to 24 bits, that kind of seems like a lot per pixel, right? But actually it ends up being not that much, and you'll see why in just a second. So, but the bit depth controls the file size, because the higher the bit depth, the larger the file, because the more bits you're using to represent each pixel. So a picture of the same size has different quality, and a picture of the same dimension will have a different file size because of how much information you're having to store for each one. Let's do an example. So here we have 1 bit depth, meaning that this image requires 781 bytes to represent, but this one here uses 16 bits per pixel, and so it's about 12 kilobytes of data, 11 kilobytes of data. Okay? Hopefully this is all intuitive, but we're stepping through to make sure we don't have any gaps in our knowledge, right? But are there any questions so far? Okay, so this is going to be a short lecture today, guys. I was really hoping we would have the computers today, but everyone's out of town that can get me the computers, not my TAs, like the people in the department. So that's okay. We can all go watch Captain Marvel together, right? No, just kidding. Okay, RGB color model. This is one of the encoding methods for storing the information about a graphics file. So RGB stands for red, green, and blue, and is based on an additive color model. So if you remember back to preschool, you probably, well, at least I did, I had like clay or Play-Doh or something of 3 different colors, right? What colors were they? Red, yellow, and blue, right? Red, yellow, blue, the primary colors, those are pigments, and when you add them together, it's not additive, it's subtractive. That's the right word. So light, when you combine this light with this light, you're adding light to light so that it gets lighter. So it's an additive color method, whereas pigments are actually absorbing light, right? The substance is absorbing light. So when you take this color and this color and add them together, what happens? Does it get lighter? No, it gets darker, right? And just like, you know, my kids, they're Play-Doh. They take this color and they match it together, and they take this, and suddenly you got brown, gross Play-Doh, right? Actually, my kids are better than that. They don't do that much. But the point stands, like if you mix a bunch of colors of Play-Doh together, it's going to be dark and brown, right? So this is not how light works. Since we're talking about images being displayed on a screen, what's so fun? Yeah, oh man, no, it's fine. Everybody does it, right? Oh no, they do. I like to speak highly of my kids because I'm very proud of them. But, sorry. So hopefully this is intuitive, but this is how light works. Different colors of light work when you combine them. Okay, so that's why we have red, green, and blue instead of red, yellow, blue. So if we take each of the individual pixels in a picture that we want to represent, using the RGB value method or the model, we would have a red value for every pixel, a green value for every pixel, and a blue value for every pixel. Right? So so each of these values represents intensity, so the amount of light. So a lower value means less intensity, less light, which means a darker color. So for example, if red is more intense, the color is perceived more towards the red side of the color spectrum. And then, so remember back when I said that 24 bits per pixel ends up not being very much? That's because in the RGB model, you need 8 bits for each of the RGB values, which only gives you values from 0 to 255. There's not a lot of variance in that. There's enough, but if you're talking about like representing real world colors, 255 values per color actually ends up not being a ton. So there's other color models that are more bits per color, and yeah. So 256 possible values for each primary color. If you've ever done any kind of web development or opened up the developer tools in your browser and inspected an element that has color, you'll see that the color values are actually represented in hexadecimal with, well, if they were bytes, it would be 3 bytes, right? So FF, 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 or R, G, and B would be white, because we can go from 0 to 255, FF is 255. So that's the maximum value that pixel can have for that color. Am I making sense, or am I talking in circles? Is this insightful for anyone? Okay, all right. When I was in high school, the only programming-ish class that they had was HTML. Not really a programming language, but it was what they had offered, and that was before Y2K. So there you go. Anyway, where am I coming? Oh, okay. So this RGB stuff is like in my blood. It's been part of how I think about light and color and stuff for so long that I forget what might or might not be intuitive. That's where I was going with that tangent. Apologize. Okay. Any questions about RGB colors? You may have heard. Oh, I'm getting ahead of myself. We'll talk about that later. Okay, so if we were to plot these 3 values kind of in a, I don't know why it's this shape, but I think it just works out with the math. That if we have, so let's start with red here. So we got 255.00 is right here, right? And then as we add green, we're going to get to 255.255.0 right here, which is yellow. As we take away red, so that we have just 0, 255.0 right here, it's going to be green, because RGB. And then we,
It's supposed to be a circle, right?
yes. So thank you. As we add blue, well, but it's hard to draw a circle with squares. So if you're going to, what it is. If you're going to map all of them, if you're going to do it in a circle, to kind of put this and this edge together, you might end up leaving out colors. So I think this is the most natural way for a lot of things. Okay, so add blue, you got 0 red, full green, full blue is cyan, this color right here. I actually don't know how to pronounce that word, so cyan? 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 No. Okay, and then as we remove green, we get closer to blue, and then we can add red to get to magenta. And then we have 0 is black, and 255, 255, 255 is white. And now you know your colors. Who knew it would take you this long, eh? Oh, okay. Okay, any questions about RGB model or anything? This is your chance. I'm starting to get a little bit loopy because I'm still just a little bit tired from being sick. And so this is your chance. If you want to see Silly Mike, yes, please. Ah, very good. So I have no idea. So you're referring to, so not all image formats store an alpha value. By the way, alpha is a 4th value that is included often with colors that represents transparency, where opacity is a better way of putting it, because when it's at 0, it's not opaque, it's completely transparent. And when it's at full 255, is completely opaque, and you can see the color as it doesn't have any transparency. Okay, so not all image storage formats support the alpha graph, right? So what we're driving at here is bitmaps. Bitmaps don't support that. PNGs do. I don't know the encoding for PNG. Is that a sufficient bad answer, non-answer for your question? Okay, great. Okay, so there's basically 3 different kinds of files, graphics files, for the purposes of this conversation. The first is bitmap images, which is just collection of dots. Vector graphics that are based on mathematical instructions. We'll talk more about each one of these in just a second. And then metafile graphics, which is a combination of these 2. So talk about bitmap versus raster. So a bitmap image is a grid of individual pixels. So each pixel, as we were just talking about, has a representation, a number, a RGB value from 0 to 255 for each pixel. And then we just line them up on a grid, and then we have, when we zoom out, we can have this little icon of an eye, right? All right, the difference between a bitmap and a raster image is that a raster, its purpose is more for printing than displaying on a screen of pixels, okay? So printers, what they want to know is where to put a dot and how much ink to put there, right? So if you think about it that way, a raster image are pixels that are stored in rows, but they have a different purpose in that their size is indicative of how much color should be in that spot. And hopefully that's intuitive, that this would be helpful for a printer that's putting little ink blots on a page. Okay. Any questions between these 2? Yeah. I'm sorry, what's the question?
I don't see like.
Oh, because you never watched a printer when you were, okay, so, or a typewriter, old school typewriter, you had the, right, okay. So you're typing, and you get to the end and you just keep going, right? This actually had, each of these pixels in a bitmap has an address associated with it, right? So you say, whereas here you're just kind of going across and these are all rows. And it's more, you're right that a grid and a set of rows is similar, but the focus is different. This is printer focus, this is screen focus. And if I answer your question, you still have some doubts, I think so. Okay. Yes?
Does a raster image only store the size of the pixel for like black and white, or how does that work? Oh,
so raster images can be for more than just black and white. I don't know raster images very well either. See how much I know, guys? I'm just like this fountain of knowledge, right? This is my extent of knowledge. I do know that you can have color raster images, but their focus is for printers. And actually, printers, because they use pigment, which is a subtractive color model, you might have seen something CMYK, which is different than RGB. Its focus is for printers because it's not an additive color model. So different. Okay, moving on. Okay, concerning quality of bitmap and raster images, there's 2 dimensions that you can use to measure the quality. The first is resolution, which means the number of pixels per unit of measurement. So example is DPI dots or pixels per inch. That's very common. So the higher the DPI, the more pixels per whatever unit you're talking about. Could be centimeter, it could be another unit, I don't know. Okay. The other thing about resolution is the higher resolution equals a sharper image because, well, for the exact reason we have here. So in this example, we don't have very many pixels per inch, so we can't, it's not very sharp. It's blurry because we don't have as many, the color is, the transitions of color between one pixel and the next are more jagged and more apparent to us than if we were zoomed out and had a higher resolution. I have no idea if I'm making sense today, guys. I apologize. Okay, the second dimension that we can measure the quality of a bitmap or raster image is by bit depth. So the number of color bits used per colored pixel. This is exactly what we were talking about earlier. So for example, 1 bit is 2 colors, 4 bits. So we kind of went all over these numbers earlier. That's how you measure image quality. Okay, vector graphics. We're almost done with these slides, so this is going to be a short day today. Who can tell me what a vector graphic is? Yeah.
It's an image that's storing like grid kind of stores like how to draw. It's like waves or like lines.
Yes, yes, very good. So we characterize the image using lines, geometric primitives instead of dots. So what this means is that instead of needing to inform the graphics processor what color to display everywhere, we just say in a mathematical form, here's this line, here's this circle, here's these geometric shapes. So we store only the calculations for drawing the lines and the shapes, and we leave it up to the graphics processor to actually do the drawing, to figure out which pixels to color a certain way when we display it on a screen. So some examples, we've got CorelDRAW, Adobe Illustrator, and Inkscape. Any of you gone up to the 4th floor in Brickyard? Ever? Okay, hopefully. And you've got 2 like wall splashes, right? The one on the left, anybody know what it is? Nobody? Yeah, CDF, the Cybersecurity and Digital Forensics, the Center for Cybersecurity and Digital Forensics. I made that logo. Using Inkscape. So yeah, I made that logo. So now all of you are going to be like, wow, and go up there, right? So I made that logo, and I used vector graphics. I used Inkscape to create a scalable vector graphic file. That's the file type. Because I knew that it needed to be able to scale, and because it's free. Anyway, okay, moving on. So these are the kinds of geometric shapes. This is a very good example because this is very pixelated, right? We're talking about vector graphics, but these are the types, this is illustrative of the types of shapes that we can describe in scalable vector graphics, right? So we can describe a cylinder or a cone or a donut, or these are the things that we can give the geometric dimensions for to be able to render something like this. So here's the difference between a raster image and a vector image. Now, no matter how much you scale this up, unless of course I scaled it up too far. Oh boy. Okay, I should make that image a little smaller so it doesn't look pixelated, because the whole point of the picture is to not look pixelated. Apologize. So this is supposed to look very clean, crisp, and have no pixels visible because it's a vector graphic, whereas this is very pixelated. So I had too great a faith in the image I was given. Okay, that's vector graphics. A couple more things. So if we were to describe a circle in a vector graphics, we would give the radius, the center, and the line and style color for the circle, and that's all that we would need. And the fill style and color, and that is all we would need to describe a circle to be rendered in an SVG, a vector graphics image file. Now, when you think about just a circle, it doesn't seem like that much information. But if you need that circle to be really huge, compare that to the number of pixels that's represented by it, and suddenly a mathematical formula seems really simple. Okay. Advantage of vector systems: the smaller file size, resizing does not change the image, and we have easy modification of the parameters so that we can do moving, scaling, rotating, and filling. And another one is actually that, at least with SVG files, it's XML. The innards of the file are XML, so you could technically go in there, modify them by hand, or use version control system on it. Awesome things like that. Yes, question?
Does it take care of the radius or the sizes relative to what's around it? Because if you give it a radius, otherwise how would it be scalable?
Oh, okay, very good. So what it does is you have a canvas size, right? And it's relative to the coordinates inside that canvas. So within, you're right that you have to have it relative to something, and the answer is whatever the canvas is that you drew it on. So it's still scalable because all you're doing is going to a certain point in the canvas and then drawing a circle or whatever it might be. And so the edges of it will still be smooth once they're rendered. Does that answer your question? Any other questions? Okay. Metafile graphics, I don't have very much experience with it all, but they basically combine raster and vector graphics, meaning you have some bitmap portion with text in there, and the advantages and disadvantages of both types apply, and then when it's enlarged, the bitmap part loses quality, whereas the vector part does not. That's pretty intuitive. Okay, let's talk about some graphics file formats, and then we should be done for the day. So the standard bitmap file formats. We have graphic. Okay, there's like some controversy on how to pronounce this. I said GIF one time to somebody, and they were like, "What?" So ever since then, I've said GIF, and I've gotten fewer confused looks. But there doesn't seem to be a 100% consensus on the internet. So basically, you know, the internet knows everything, but it doesn't know how to pronounce stuff. It's crazy. What's up with that? We've got JPEGs, TIFFs, GMPs, or bumps. No, just kidding. Standard vector file formats, HPGL, AutoCAD, DXF. We also have some non-standard graphics file format. I don't know why we're putting this under non-standard because, let's see, here's SVG. It's pretty, I guess it's semi-standard. Photoshop, that's Illustrator, those are pretty standard. So don't ask me. Don't worry, I won't ask you what's the difference between standard and non-standard vector file formats. I don't know. All right, data compression. So some image formats compress their data, and that's how they get. So if you think about a bitmap, which is just that grid of RGB values for each pixel, right? That is what a bitmap is. It maps each of the bits to a pixel, right? If you get over that, what some image format creators decided to do was to just compress the data. It's not that simplistic, but that's the essence of it. So that's how we got JPEGs and PNGs. Bitmaps, of course, do not compress their data. Yeah, okay, so basically it comes down to two different types of data compression, lossless and lossy. The difference, of course, is just like with other lossy and lossless stuff. Lossless reduces the file without removing data. How do you do that? Well, these smart people know, but I don't, so that's cool. Basically, let's say you have 200 red bytes. You just represent it as 1 byte for the red color and 1 byte for the specification of 200 red bytes. So that's a pretty standard compression approach, data compression approach. So they just applied that to image files. And then lossy compression, JPEG is one of the most common formats of lossy compression formats, where we permanently discard bits of information using some vector quantization. So based on some vectors in the graphics file, it will discard some data. So if I understand correctly, which I might be off here, which is why it's not on the slide, and I'm not going to test you on it. One of the things that JPEGs do is they say, okay, here's like this point of color. I'm going to like push it a certain depth, right? And that's going to determine how. No, scratch that. I'm not going there because I can't explain it. Okay, lossless versus lossy. This is also very intuitive. Lossless produces an exact replica of the original. Lossy is an altered replica of the data. So I don't know if you've ever played with this when creating JPEGs, but you can vary the amount of compression you want when you create the image. And so if you want it really compressed, and you actually get what are called JPEG artifacts, which is it trying to do a good job of replicating the colors it's trying to do it in the most efficient manner. And so you get all these like weird colors that don't make sense sometimes. There was a group that I'm remembering a paper on image forensics that analyzed just JPEG artifacts. Because they took a JPEG and then they converted that JPEG into a JPEG over and over and over again, just to figure out what would happen when they created a JPEG, as far as like creating artifacts, to study the patterns so that you could recover data. Like this is a whole thing. This is the thing in forensics is figuring out how to better analyze image files for the purpose of figuring out where it came from, figure out if it's been altered, things like that. Those are important if you're going to use a picture as evidence to know all that information. Okay. Digital. Did I just trigger? Okay, sorry. Okay. Digital camera file formats. What this sentence is just saying is criminals might take pictures. Okay, that's what it really means, to identify victims, discover additional evidence, completeness, completeness. Okay, examining the raw file format. So I don't know if you've ever heard about the raw file format, but really high-end cameras support raw image formats, and it's referred to as a digital negative because the sensors in the actual digital camera, they just record the pixels on the memory's camera card. So inside a camera, there's these digital light sensors that get converted into an image, right? So just like this says, sorry I'm saying what it says again, but those sensors, the raw data that comes off of those sensors, that if you were to just take that and store it, that's the raw image file. What that means is that a camera of this brand and a camera of this brand, their raw file formats might be completely different because their sensors are different. So raw file format maintains the best picture quality, but a lot of times it's proprietary, just like I said. Not all image viewers can display these formats. And then the process of converting raw pictures to another format is called, referred to as demosaicing. That's the word of the day, demosaicing. Okay, last subtopic, okay? I know I promised an eat early out, and you're like, come on, we're done listening to you. Okay, EXIF. EXIF is one of the most important things about image forensics. Did everybody hear what I just said? EXIF is one of the most important parts of image forensics, okay? Because this is how we store metadata. Okay? Pretty much, it really only applies to JPEG images. But if you take a JPEG image and put a whole bunch of metadata at the front, it's now an EXIF image, not necessarily a JPEG. Strictly speaking, it's still, it's really just an EXIF. It's runs metadata at the beginning of the file. If you've ever been on your computer and like right-click on an image and gone to like properties or something and have all this information about like the make and the model and maybe the latitude and longitude, all of that, that's it data. Cool, right? Okay. Here's an example. Any questions? Yes.
Is it just a wrapper around JPEG and like TIFF? Because if it is, can't you strip off like this game?
Yes and no. So when we get around to doing the image lab, one thing that you'll experience is that at the very first few bytes in a JPEG image, they have to be a certain sequence of bytes to tell the operating system that it is a JPEG image. Okay? That sequence of bytes is slightly different, and then it's basically just ASCII text. So is it a wrapper? Well, kind of, but it doesn't change anything on the inside, right? So that's one way of thinking about it, but yes.
Just like, so if you take a picture with your digital camera and it's excellent, but let's say you didn't want this metadata for whatever reason, could you go into like a hex editor and like strip out all of the bytes that say that it's an EXIF and then replace it with a couple bytes that just say it's a JPEG?
Yes.
You won't have to say.
Yes. Yeah. So just to repeat for those watching this on YouTube later, the comment was that if you have an image that has all this EXIF data in it, but you don't want that metadata, can you just go in there, pull out, delete all the EXIF metadata file or fields, and replace whatever bytes you need to? This actually called the magic number. That those bytes that tell the operating system that it's a JPEG, it's called a magic number. Put the right magic number in there, it will be a JPEG, a valid JPEG. So yes. Any other questions? So what's the most important part about image forensics? EXIF data. And what is it? It's metadata in a JPEG. Okay, all right. And that's all I got for you, and we'll see you on Tuesday.